And I should have checked, hold on a second, oops, got to get this out of the way. That all looks right, so I think we're good to go. So let's try it. So guys, today what we're going to do is we're going to talk about the whys. Why is it that some things are strong acids? Why are some things weak acids? Why are some things alcohols? And why are some things just non-electrolytes that don't do anything? So guys, we're going to talk about all of this today. We're going to talk a little bit about Matt's thought about what is the Ka of HF and why. And it makes for an interesting day. So here's the way today's going to roll out, and I really don't think you need to write any of this down, but just setting the stage. Here's where we're at. We have talked about acids and bases. We've talked about strong acids and bases, weak acids and bases, and then we took that weak acid-base conversation and we invited salt solutions into the conversation, which is where we then talked about this idea of lineage, right? And we talked about the idea that if a salt comes from strong acid-base parents, the pH will be 7. If a salt comes from acid-base parents that are not strong acids or bases, there's that logical progression that then allows us to figure out pH. Is that all coming back to you? It's kind of where we are right now. Okay, so guys, moving forward, here's what we're going to do. We're going to answer this question. The question is why? So what do all 5 of these compounds have in common? And the answer is they all contain hydrogen, right? But here's the question we're going to pick at. Why is this a strong acid? Why is this a weak acid? Why is this a base? Why is this a weak acid? And why is this an alcohol? Because guys, you'll notice that it's not just as simple as each one of these things contains hydrogen. I mean, it really is that simple here, right? But if you look at the last 3, what do the last 3 have in common? Because it's not just hydrogen. It's OH. So guys, when we ask and answer this question about why do they behave as they do, part of the answer is going to revolve around hydrogen interacting with other things. But eventually it's going to come down to hydrogen interacting with oxygen interacting with other things. So follow that. So here we've got an oxygen bonded to a hydrogen bonded to an Na. Here we've got an oxygen bond or a hydrogen bonded to an oxygen bonded to a carbon that is also double bonded to an oxygen bonded to another carbon. And here we've got an hydrogen bonded to an oxygen bonded to a carbon that then bonded to 3 hydrogens. So why do these behave so radically different? So guys, we're going to answer all of these questions. But to do it, the first thing we've got to do is set the stage. We've got to talk about what are the factors that influence how these hydrogens behave in the first place. So guys, what I'm going to do is I'm going to fill up your toolbox with some ideas about how hydrogen interacts with other atoms. Then we're going to bring those ideas to bear in different ways for each one of these molecules to understand how this works. Does that make sense? So again, we're going to talk about some general principles, then we're going to apply those principles in each one of these unique settings and understand why they're strong acids, weak acids, alcohols, and so on. You good? Okay, so guys, to get started, let me give you the background. This you obviously want to write down. So, oops, hold on, I'm drawing dots. There we go. Okay, so guys, in order to have this conversation, what we need to do is we need to talk about what they call the H star bond. And as you might know, well, you probably don't know, there was a day in computer coding when star actually meant wild card. Any of you know about that? Never mind. Doesn't matter. So guys, star is simply a wild card that represents some other particle. It could be a halogen, it could be an oxygen, it's just something else. So it's some other atom. So as we understand why acids are bases, acids are acids and bases are bases, and weak acids are weak acids and strong acids are strong acids, what we really need to do, guys, is we've got to focus on this bond right here. So our focus is on the bond. You okay? So let's lay out the general principles. Guys, what is going to be true of an acid if that bond breaks and never reforms? Strong acid. What is going to be true of an acid if that bond breaks, but then also can reform? Then it's a weak acid. What happens if that bond doesn't break at all? Well, maybe. It could also be a non-electrolyte, and that would make it an alcohol. So guys, what you're going to find out is that the likelihood, for lack of a better term, the likelihood that that bond breaks and the likelihood that that bond reforms determines whether this molecule will be an acid, strong acid, or a weak acid, or an alcohol. So what we're doing is focusing on that bond, but what we're really doing is talking about how well does that bond break. And guys, what you're going to find out is that there are 3 factors that we need to keep track of in order to figure out how that bond behaves. So guys, what I'm going to do is I'm going to give you these 3 factors, and we're not going to explain them. We're not going to qualify them. I'm just going to give them to you. And then what we're going to do is we're going to bring these 3 factors as a lens through which we're going to look at HCl, HF, things like that. And we're going to understand how these factors apply differently in different circumstances. But again, guys, make sure you're clear on this idea. Why do we care about this bond? Because this bond determines the strength of the acid. If it breaks easy, it'll be strong. If it breaks but reforms, it'll be weak. If it doesn't break at all, it'll be an alcohol. Does that make sense? Okay, so what are the factors? Well, guys, factor number 1 is the polarity of the H star bond. And guys, I was thinking about this morning as I was just thinking about the way my day was going to roll out. And I want to add a thought to this. And I just want to share this with you. Because what you're going to find is that 2 of these factors get a little confusing. So I just added this, and I want to see if this clarifies it all, but we won't know until we get to the end of this, but let's try. So guys, when we talk about the polarity of this bond, what we're talking about is how shifted it is. So picture, if you can, for a minute, what is a covalent, and these are all covalent bonds. So guys, what does a covalent bond look like? What are the important concepts that we've talked about? So shared, where does that sharing happen? Between the 2 nuclei. What does it create? There's a very elaborate name that we have for that. Do you remember? Say it again, you got it. Not field, but region. So we call that the region of increased electron density. Guys, as I'm redoing my notes, would now be a good time to bring up a picture of that? Or can you picture it? Do you know what I'm saying? So when we think covalent bond, we think region of increased electron density. So what does that have to do with polarity? Well, guys, the idea is that region of increased electron density can shift towards one atom or the other, right? What determines which direction it shifts? The electronegativity. So it will shift towards the atom that is more electronegative, right? That creates polarities and everything that we've talked about, right? Is that all coming back to you? Okay, so guys, what then is the relationship between the polarity of the H star bond and the strength of the acid? And guys, it's simply this. The more polar the bond is, the stronger the acid is. So guys, can we talk about why? Why would that be true? Why would more polar bonds form stronger acids? What has to be true of those more polar bonds? Let's do my question first. So guys, what has to be true of a more polar bond if a more polar bond creates a stronger acid? It has to be, what do you mean by weaker? You're right, but go that. Stop right there. That's the point. Guys, more polar bonds are more easily broken. Does that make sense? That's the underlying truth. That if you have a bond with a greater polarity, that more polar bond will be weaker, and because it's weaker, it's more easily broken, giving away more hydrogens, making the acid stronger. Do you need a second to maybe jot those additional thoughts down, or does that just make sense intuitively? But that's the underlying logic, that the more shifted the bond is, the more readily that bond is broken, and as a result, the more easily that hydrogen is given away, making the acid stronger. Go ahead. Hold on, can you wait just 1 second? Do you hear voices? I wonder if... No, those are sometimes similar. Nope, it's a construction crew.
Really? It sounds like teenage girls.
Oh, if you looked, it's not teenage girls. It's large men in work boots. Go ahead, Brandon. No, this is the hydrogen bonded to something else. So let's go back here just really quick. So what do all acids have in common? Well, they all contain hydrogen. So this is the H star bond. 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 So it's H bonded to something else. And what we just found out is the more polar that H star bond is, the more readily it'll be broken and the stronger the acid is. Is that okay? Is that helpful? Okay. So guys, are you okay with that first fundamental idea that polarity is a predictor of strength? The more polar the bond, the stronger the acid, because the bond breaks more readily. Is that okay? Yeah. Let's not talk examples yet. That's where this is going. But so Gwen's mind is going, okay, then let's talk about hydrofluoric acid. What you're going to find out is there's 3 factors, right? And each of these factors don't apply equally in all cases. It turns out the strength of hydrofluoric acid has nothing to do with the polarity of the bond. So we've got to do all 3 factors before we can talk about any examples, okay? So guys, factor number 2 is the strength of the HX bond. And guys, this is where I've run into trouble, because people incorrectly associate strength with polarity. They are different. So I'd like you to write this down, and then I'd like to try to draw a picture, understanding again that I'm the worst artist, at least on 3rd floor. But you may find the picture helpful. So guys, picture, and I would encourage you to do this with me. So we're going to go nucleus, and what I want to try to do is help you understand the difference between polarity and strength. So guys, we're going to draw the region of increased electron density, okay? So if we have, let's say that this has a high electronegativity and this has a low electronegativity. So guys, when we draw a region of increased electron density, where are we going to draw it? In the middle? Where will it be? Shifted towards the left. So our region of increased electron density is going to be shifted towards the more electronegative element. So that is a reflection or a image of polarity. But guys, that has nothing to do with strength. Strength is a different factor altogether. So what determines the strength of the bond? And guys, you may remember there's a lot of forces at play here. Can we talk about them? What are the forces at play? The attraction of the nucleus towards the region of increased electron density. But that's not the only factor at play to determine strength. What is the other ones? The repulsion of the nuclei on each other and the repulsion of the electrons on each other. So guys, understand the strength of the bond is the resolution of all of those forces. And functionally, it is not dependent upon polarity. What is it dependent upon? We'll talk in a minute. But guys, understand polarity and strength are not the same thing. Polarity is how shifted the electrons are. Strength is how attracted the atoms are to each other, which is dependent upon the attraction of the nuclei for that region of increased electron density minus the repulsion between the two nuclei. Do you see the distinction? Is that okay? So guys, then the question becomes this. What is the relationship between strength and acidic strength? And it's this. The weaker the bond, the stronger the acid. And then guys, we've got one more factor that we need to talk about, and then we're going to dig in and start talking about specifics. You guys are a little unsure of yourselves right now, right? You're going, ooh, wait a second, polarity, and I understand more polar bonds break more readily, and now I've got this thing called strength, and the stronger the bond, the less likely the bonds will break, but I'm not quite sure if I understand the difference between strength and polarity, and now we've got these worthless drawings that Knappenberger's thrown in front of us, and I'm not quite sure. Guys, if you're comfortable with the idea that polarity is shifting, strength is attraction, and that both of those things influence acidic strength, so the more shifted the bond, polarity, the stronger the acid, and the stronger the attraction, the stronger the bond, the weaker the acid, because it breaks apart less easily, you're right where you need to be. So guys, given those two fundamental truths, are you okay? Okay, I'm going to give you factor number 3. Factor number 3 is the stability of the conjugate base. That conjugate base is star minus. Hey.
Hey, there'll be a little bit of noise this afternoon.
Yeah.
Not a lot.
No. Yeah, you guys are, and actually, I'm going to be done in 30 minutes, and I'm done teaching for the rest of the day. I tell you what, I know. I'm one of the chosen one. No, I have 4th period prep, so.
You did your prep. Okay.
Exactly.
So we're going to be, today and tomorrow, we'll have all the inside stuff done.
Oh, great.
We're just waiting for our crews to come and do the stuff on the roof.
Okay.
We wanted to get all the inside done.
Thank you. That's wonderful. So dig in.
And then when it's all done, we'll teach you. It's going to be on the 30-minute timer.
Yeah,
So
right.
if you guys are working in there, no one will forget to turn it off.
That's awesome.
It'll shut off in a half hour.
Thank you. Where are you going to do the drop for the timer?
It's going to be right there in the corner.
Okay, sounds great.
You know where the gas, is your gas turn on and off?
Uh-huh, yeah.
Right on.
Oh, wonderful.
So it's
Sounds
all right there.
perfect. Thank you so
And I'll
much.
make it all the way to 142.
Perfect.
Okay?
Thank you. Yep. Yeah, he's one of the district HVAC contractors. So guys, stability of the conjugate base. And remember, conjugate bases like acetate ion would be CH3COO minus, because remember when you lose the hydrogen, the conjugate base takes on a negative charge. But guys, the relationship is this. The more stable the conjugate base is, the stronger the acid. We've already kind of got something like CH3COOH. If we've got something like this, this does go backwards. It does reach equilibrium, but we're going to talk in a minute about the idea that this acetate ion is actually stabilized We'll talk about it in a minute. It's resonance stabilized. It contains delocalized pi bonding. And as a result, this acid is stronger than it would be if that weren't the case. And we'll talk more in a minute. So guys, these are our three factors. Just tuck them away in your head. What determines the strength of the acid? It's all about the H star bond. So what determines the strength of the acid? It's the polarity of the bond, the strength of the bond, and then we'll talk later about the stability of the conjugate base. But for now, the really important pieces are the polarity of the bond and the strength of the bond. Given that foundation, can we move on? Ready to go? Okay. So guys, here we go. We are now going to talk about two classes of acids. The first one are what are called the binary acids. Scratch it down with me. So guys, what does bi mean? Two, right? So binary acids are acids that contain two parts. If one of those parts is hydrogen, we're only left with one other thing. So guys, the binary acids are acids that are composed of hydrogen and another type of atom. Many times that atom is a halogen. Gwen, can you see how we're leading towards your question? We're talking HCl, HI, HBr, HF. HH. So guys, what determines the strength of these bonds? Or these acids. So these are what we call the HX acids, where X is this other component. So you ready? I'm just going to lay it out there before you. What determines the strength of a binary acid? Is it the strength of the bond, the H star bond, or is it the polarity of the H star bond? And guys, it turns out it's strength. The strength of a binary acid depends most on the strength of the HX bond. That's it. That's why hydrofluoric acid is weak, because the bond is so strong. But we need to do way better than that. Brandon, before you do questions, let me get you fully through this idea, then we'll look at some examples and see where we're at. So guys, the relationship is this. The stronger the HX bond, the weaker the acid. And that makes sense, right? The stronger the bond is, the less likely it breaks. Yes. And we're actually going to look at that. Yeah, and that's why we can't really draw a line, because we measure strength by Ka, and functionally the Ka is undefined because you're dividing by 0. Wait, products divided by reactants dividing by 0. Yeah. So guys, it goes like this then. We need to talk about how this rule applies, and I love what you're doing. Does this mean that HCl is stronger than HBr, things like that? Guys, it goes like this. Within a group, the HX bond weakens as X gets bigger. And that makes a stronger acid. So let's say it again. Within a group, the HX bond gets weaker as X gets bigger. We'll talk about why in a minute. But as X gets bigger, the HX bond gets weaker and the acid gets stronger. Tell me when you're ready, because I want to show you. No, it sizes in radius. Yeah, and that's a great question. Isabel says, is it sizes in mass? And it's not, although they're frankly directly related. But it sizes in radius. And I heard one of you say shielding a minute ago. Guys, check this out. So let's do, hey, there's our picture. So let me muck with this in green. So guys, this is going to be our hydrogen. Okay, now let's do this. Let's say that this atom is now fluorine. So guys, fluorine's valence electrons are in the second energy level. So we have one energy level worth of shielding right here. This nucleus can reach out to that region of increased electron density pretty easily. It forms a strong bond. That bond is hard to break, and consequently, that's a weak acid. Now guys, let's replace this. Let's go all the way down to iodine. Guys, I'm going to have to redraw this radically, because if this is iodine, I don't like the way I did this. If this is iodine, the nucleus for iodine would be like way over here, and we've got 1, 2, 3, 4, 1, 2, 3, 4 energy levels of electrons for this nucleus to reach through in order to grab a hold of that region of increased electron density. You know that is shielding. So guys, in these big old atoms like iodine and bromine and chlorine, there's so much shielding in here that that nucleus can't grab a hold of that shared pair of electrons very well. That weakens this bond, making it more easily broken and making the acid stronger. Do you see how that works? So the bigger the atom, the weaker the bond because of that increased shielding. The bigger the atom, the weaker the bond, the stronger the acid. Now notice, and Daniel pointed this out, within the halogens it's a very clean line, because anything below from chlorine down, they all just break completely apart. All of these bonds are so weak that they all just break completely apart. The only one that's actually strong enough to have some longevity is the HF bond, and that's why HF is a weak acid. Does that make sense? But guys, understand that this trend holds not just in this example. What about H2S and H2O? We just talked about HCl and HF. But guys, what about H2S and H2O? Which one will be the stronger acid? So, and let me draw their Lewis dot structures if this is helpful. So guys, now we've got hydrogen sulfide, which is that yucky, stinky gas, that rotten egg smell, and we've got water. Which one will be the stronger acid? Well, let's talk. We've got binary acids. We've got hydrogens bonded to one other atom. Notice there's multiple hydrogens, but it's still one type of atom. So these are still binary acids. So we need to look at sulfur and oxygen. Notice they're group mates. So which one's bigger, oxygen or sulfur? Right, as we go down, they always get bigger. So if sulfur is bigger, what will be true of its bonds to hydrogen? Weaker. And if its bonds to hydrogen are weaker, what will be true of its acidic strength? Stronger. So the stronger acid between H2S and H2O would be H2S. Does that reasoning make sense? Is that okay? Okay, but guys, understand the logic that I just explained to you only works in groups. What about across periods? Well, guys, a secondary predictor of bond strength is actually polarity. Now, guys, as we've already established, the strength of an acid increases as the polarity of the bond increases. And the polarity of the bond increases as the electronegativity of the element that hydrogen is bonded to increases. So, the strength of the acid increases as the electronegativity of X goes up. Again, it's more shifted, and consequently it's weaker. So let me show you an example to make sure that you understand the principle. You okay? So guys, which is a stronger acid? NH3 or CH4? Again, NH3 or CH4? Which is the stronger acid? Okay, so let's look. So guys, we've got this. I'll draw them here. We've got NH3 and we've got CH4. So guys, what we need to know to figure out the strength of these molecules, the acidic strength of these molecules, is we need to know the polarities of the bonds. Notice that nitrogen and carbon are they're period mates. So their sizes are pretty close to the same. So guys, when we're dealing with elements that are in the same period, they functionally have the same amount of shielding. So to figure out which one is the stronger acid, we need to know which bond is more polar. So both of them are bonded to hydrogen, of course, but guys, which element is more electronegative, nitrogen or carbon? As we move to the right, they get stronger, right? So guys, this molecule will have more polar bonds with hydrogen. Does that make sense? So the bonds with hydrogen will be more polar. Therefore, they break more readily. Therefore, NH3 will be the stronger acid. Does that make sense? Okay, now you're thinking, wait, I thought NH3 is a base. But remember what we said. When we say NH3 is a base, we mean basic towards what? Towards water. But now we're not even talking about water. It turns out that NH3 is more acidic than CH4. Neither one of them is acidic compared to water, but we actually we can say that NH3 is more acidic than CH4, and it's all because of the polarity of the bonds. Does that make sense? Okay, so now guys, try this. Here's the hard one. Which is more acidic? NH3 or SiH4? Right, and that, do you see the problem? Do you mind if I do this? No, I won't step on your jacket. I just need to be able. Okay, so guys, the problem is this. We're looking at NH3. Hey, John, would you just leave it for me? Thank you. So guys, we're looking at NH3 and SiH4. Do you see how we have competing issues? So SiH4 is below NH3. Would that make it stronger or weaker? Stronger because it's bigger, right? Silicon is physically bigger than nitrogen. Because silicon is bigger, it forms weaker bonds, stronger acid. So based upon position vertically, Si would be stronger acid. But guys, notice that nitrogen is to the right, making it more electronegative, thereby suggesting that these bonds would be more polar and therefore stronger acid. So which wins? Is it the strength difference because silicon is bigger, or is it the polarity difference because nitrogen is stronger? Which one predominates? It's the strength issue. So strength always trumps polarity, so SiH4 would be the stronger acid. Am I the only person that, as I was saying that out loud, it started to sound like Vicini talking in a Princess Bride about never start a land war in Asia? Certainly, I could choose the cup in front of you. Anyway, so guys, Si is bigger, right? So Si is the stronger acid. Is that, you get the idea? Is that okay? Okay. So guys, we are now done with the binary acids. So guys, there's actually only one other type of acid we need to talk about. And that is, and are you okay with this, that the strength, do you need to write it down or are you okay? You already wrote it down. Okay. What's that?
Because HF is very polar, but it's a strong enough bond.
Did you hear that? That fully explains why HF is a weak acid, because you're right. That bond between H and F is wildly polar. It's almost bordering on ionic. It's so polar, but it's also so strong, and strong trumps polar. Yeah, that's a great point, Matt. I'm glad you said that. Are we good? We good? Okay, so guys, the next one, the last one, the only other type of acid that exists in our world are what are called the oxyacids. By what? So we are not going to talk about Lewis acids and bases. Yeah, our AP chemistry world. Because we're not talking about Lewis acids and bases, although we are going to talk briefly at the end of this about Lewis acids and bases. Excluding Lewis acids and bases, this list then becomes pretty exhaustive. Acids can be thought of as either binary or oxy. So, guys, when we talk about oxyacids, what element do we need to now bring into the conversation? Oxygen, right? So, oxyacids are acids that contain more than one or more OH groups. Now, guys, you ready for a deep thought? This may be ahead of you, but I'm going to try it and see how it goes. Ready? So the thinking goes like this. In an oxyacid, the hydrogen has got to be bonded to an oxygen. Is that okay? That oxygen becomes a given. The oxygen is always there. They're oxyacids. The oxygen is always there, and the hydrogen is always bonded to it. This means that strength is no longer a determining factor. Bond strength. This means bond strength is no longer a determining factor in the strength of the acids. Why not? Because you're always bonded to oxygen, and that bond will always have the same strength, but not always the same polarity. Let me say why, right? But guys, did you understand the thought? Our hydrogen is always bonded to oxygen. Because oxygen is now a given, the strength of that bond will always be the same. The strength of the bond between oxygen and hydrogen is fixed. It doesn't change. So the strength of the bond will always be the same, but the polarity of the bond will not always be the same. So how can that be? Well, guys, the answer is what's bonded over here. Because the stuff that's bonded on the other side of the oxygen can actually change the polarity of the bond. And that's what we're going to talk about. You ready? It goes like this. So guys, when we talk about oxyacids, we need to understand that these OH also exist in bases. So why are some things strong or weak acids? Why are some of them bases? Why are some of them alcohols? Functionally, the question we're asking is this. What determines whether this OH group will be acidic, basic, or an alcohol? And the answer is this. And guys, I would just encourage you, stop for a second. It all has to do with what we call Y. And it goes like this. This is what you want to write down. YOH. So guys, this is what we've just established. The strength, I'm sick of green. The strength of this bond is always the same. Why? Why is the strength of that bond always the same? It's always hydrogen bonded to oxygen. These are oxyacids. But guys, the polarity of that bond is not always the same. And why is that true? Because Y changes. And guys, it turns out that the polarity of a bond is not just a function of the electronegativities of the elements that form the bond. It turns out that sometimes elements can be bonded further down the row in the molecule, and they can actually affect the polarity of neighboring bonds based simply on the fact that these guys are highly electronegative. It's a new idea, but the idea is this: the polarity of a bond is not just a function of the two atoms that form the bond. The polarity of the bond can also be affected by the other atoms that are bonded nearby. And that's what we're going to talk about now. You ready to go? Okay, so it goes like this. Guys, let's look at some examples. Example number 1 is this. What if Y is a metal? What if Y is a metal? So let's replace Y with sodium. What do you know about the electronegativities of metals? Very low, right? So is sodium going to be strong enough to create a greater polarity in that bond? No, sodium is super weak. How weak is sodium? Guys, sodium is so weak that oxygen steals its electron. This becomes negative, that becomes positive, and we just made the salt sodium hydroxide. And what do we know that salt to be? A strong base. So guys, if Y is a metal, that metal is so weak, it's a metal, that metal is so weak that the oxygen steals the electron from the metal. That forms an ionic bond, and that makes the substance basic. So the idea in summary goes like this. If Y is a metal, it has a low electronegativity. If that's the case, the electron is completely transferred to the oxygen. This forms hydroxide ion. That makes a hydroxide salt, which is basic. You okay with that idea? So anytime you have a metal bonded to an OH, it's going to be a base. How you doing? You good? Okay, so now guys, what about if Y is a nonmetal? Well, guys, if Y is a nonmetal, nonmetals are strong. Oxygen cannot steal an electron from a nonmetal. Consequently, the bond between Y and O is covalent. As a result, that bond doesn't break very well and OH is not formed. These are not bases. So guys, if they're not bases, these things are either going to be weak acids or they're going to be alcohols. They're either going to be acidic, weak acids, or they're going to be alcohols. And guys, understand an alcohol is just a substance that doesn't give away hydrogen at all. Is this getting a little murky for you? Let's just write it down, and then guys, we'll show you pictures, and the pictures help a lot. So guys, what determines if this is going to be a weak acid or an alcohol? And it all comes down to something called drift. Just write it down with me and I'll show you pictures. So as the electronegativity of Y increases, the acidity increases due to something called drift. Drift is the process of making this OH bond more polar. And I'm going to show you a picture of what I'm talking about in just a second, and it'll make sense. So guys, I know right now you're going, whoa. Just check this out. You guys all caught up? Can I show you a picture? So let me get in writing mode and then let me show you a picture. Oh wait, I can't do that because then I can't bring in the picture. There we go. So guys, here we have two oxyacids. This oxyacid is ClOH. This oxyacid is IOH. So how do we know they're oxyacids? Well, let's think about it. We've got hydrogen bonded to oxygen, so it could be an oxyacid. But how do we know that it's an oxyacid? Well, we know because we look here, and the chlorine and the iodine are nonmetals. So that tells us that this is probably, it's either going to be an oxyacid or it's going to be an alcohol. But guys, here's what happens. The strength of this acid is determined by how easily that bond breaks. So, what is it that determines how easily that bond's going to break? And the answer is the polarity of the bond. So this is what drift is all about. We've got this region of increased electron density. And it is shifted towards the oxygen because oxygen is more electronegative than hydrogen. But guys, it turns out that that's not the only force that causes the shifting. This chlorine also gets involved. And this chlorine has an electronegativity of 3. It's very electronegative. And what happens is this chlorine reaches, its nucleus reaches around the oxygen nuclei, grabs a hold of this region of increased electron density, and causes it to drift or shift even more than just the oxygen causes it to shift. And because that region of increased electron density shifts even more, it makes this bond even polar and more likely to break. Now guys, understand the same thing happens down here. We've got this region of increased electron density, and the iodine nucleus also pulls on those electrons. But the electronegativity of iodine is only 2.5. And because it's lower, it doesn't cause as much drift. This bond is less polar, and therefore this acid is weaker because the bond doesn't break as readily. So here we've got a lot of drift. This bond breaks really pretty easily, and the Ka for this acid is here. Notice it's not terribly strong, but guys, notice here, less drift. This bond does not break as easily, and as a result, that acid is actually 1,000 times weaker based upon its Ka. Does that make sense? Do you understand now the idea behind drift? Yeah? That's a good question. All of them, all atoms, except for the metals, all non-metals will do this to a point. You will never be asked to differentiate. They will never come to you and say, with the oxyacids, with the binary acids, they will ask you to say which one's stronger or weaker. With the oxyacids, they could give you 2 oxyacids and say which one's stronger, which one's weaker. But they wouldn't give you an oxyacid and an alcohol and say which one of these do you think is the alcohol. Well, they would never give you a molecule and say, is this an oxyacid or an alcohol? You don't need to know where that line exists, but you do need to know that there is a line that exists, and if this atom is strong enough, it'll create enough drift that it'll function as an acid. If this atom is not strong enough, it won't create enough drift, and you get an alcohol. And we'll talk about that in just a second. So you won't have to know where that line is, but you will have to explain the line if they give you the answer. Does that make sense? Go ahead, Brent. Well, so you need to understand the concept of drift. So they could come to you and they could say, why is ClOH a stronger acid than IOH? You would say that chlorine is a more electronegative element, creating more drift in the oxygen-hydrogen bond, making it more easily broken, therefore creating a stronger acid. They would never do this. They would never come to you and say, is IOH a weak acid or an alcohol? That's what they wouldn't do. But they could ask you to do this comparatively. Is that okay?
Yeah.
Go ahead.
So, I don't know. Is there an element of drift where the chlorine holds its bonded pair, like its region of electrons?
Right.
Closer to the chlorine, and that later affects, like, the OHs.
Like, does this bond become so polar that it breaks?
No, I'm saying does a ClO, this region of electron density, move over to the Cl, and then because that one's moved over, does that in turn move the OH?
Well, and that's actually what's happening. That we've also got this region of increased electron density here, which is shifted, and this one is shifted. So chlorine's pulling them all this way. Yeah, they're all moving. I actually, it's really cool the way they can map this now. Remind me at the end of the class, and we'll look it up, because they can actually now do computer rendered electron density maps of molecules. Let's look it up when we're done. I know I'll forget, but let's look it up. So guys, you okay with the idea? So now let's take that and let's apply this idea in a new setting. And it's this. Scratch this down with me. Guys, it turns out that sometimes, and all you need to do is draw this. It turns out that sometimes this whole conversation even gets even more interesting, because not only can Y affect the polarity of the OH bond, but so can the things bonded to Y. And many times those things are oxygen atoms. So what happens is this element right here many times is a carbon. Carbon is not terribly electronegative. Carbon is not electronegative to create enough drift here to weaken this bond. But if there's an oxygen over here, it turns out that this oxygen is electronegative enough to create enough drift to polarize that bond enough that it actually causes that bond to break, just a moment, and forms a weak acid. And guys, there's a name for this, and this you actually do want to write down. This guy, draw it with me. This is what is called a carboxylic acid group. And Matt, I see you, but I want to get to this before we do questions. So guys, this is what is called a carboxylic acid group, or maybe you've learned this as what's called the carbonyl group, or even a carboxyl group. But guys, functionally it's just written as COOH. And I'll give you a second to catch up with me, and then we need to talk. You guys caught up? So guys, why is that hydrogen acidic? What's more electronegative? The other oxygen. So guys, the word drift is fair game on the AP test. So why is that hydrogen acidic? The answer is the drift caused by this oxygen. It's not the carbon. This oxygen actually causes drift, which increases the polarity of this bond and makes that bond more readily broken. Now, guys, the interesting question is, why do we care? And the answer is because every single molecule that you know to be biologic and acidic contains this. So if we put a hydrogen here, guess what we just made? Ant spit. This is formic acid. If we take that off, and if we put this over here, now we just made vinegar. But guys, it doesn't stop there. If we tag, and you'll find out in organic chemistry, they call these R groups. If we tag the right R group on this, you can make lactic acid, citric acid, deoxyribonucleic acid, DNA. Guys, every single organic molecule that exists that is acidic contains this group. And the whole reason those things are acidic is because of the drift that is created by that oxygen on the other side of the carbon. So this is a wildly important thing to understand because it explains why every single organic substance that is acidic is acidic. So it's important to keep track of. And that's the point. It contains carbon. So guys, all of these organic acetylsalicylic acid, you know what that is? It's actually aspirin. And we're going to be titrating that in a couple weeks. Go ahead.
So, I have a question about that. So it's not, is it like the oxygen? For some reason I just keep picturing like this, like the oxygen is shifting the electron density between itself and the carbon, which makes it, so the carbon is like able to pull, like it just kind of pulls everything over, which then.
But it's not a function of the carbon because oxygen is more electronegative than carbon.
Yeah, that's why I get so confused, because how does that oxygen reach all the way?
Yeah. Right, and the answer is it does. Because this is the problem with the way that we represent molecules. We think of them as being very sterile entities, particles that have lines that represent bonds, letters that represent atoms. When in fact what we've got is we've got 8 protons here, 6 protons here, 8 protons here, 1 proton here, and we've got electrons going crazy. Quantum theory stupidness. And these protons over here are strong enough that there's this place of positivity right here that is so positive that it causes even these electrons that are doing their 1s1 causes them to shift. It's all about positives attracting negatives. And these positives are strong enough that it calls those negatives over enough that it makes that bond more easily broken. Yeah, crazy, right? Yeah, go ahead.
So it's not, what, this is the question I was going to ask. So it's not oxygen pulls on carbons and then carbon.
No, it's not like, yeah, it's not like a chain, although there could be some of that, because if these electrons are going to move over here, it would be easier if these electrons were moved. So it does cause them all to drift. It's not just these, they all drift. But because this is the end of the line, it really affects the polarity of that bond because they're all moving away from there. Is that okay? Okay. So guys, one other thing to sprinkle in really quickly and then we're going to wrap this up. Guys, here's the other thing we need to talk about, why these acids are acidic. So do this with me. Let's go oxygen, double bond carbon, oxygen, hydrogen, bump, 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 like this. Now guys, watch this. When this functions as an acid, this goes away, right? But now do you see what happened? These oxygens and so this electron, oh gosh, this electron stayed, right? The hydrogen went away as a positive ion, the electron stayed. Guys, do you see what just happened? These oxygens are now equivalent, and we could just as easily see that? Sound familiar? Delocalized pi bonding. So when you pull the hydrogen off of that oxygen, these two oxygens become equivalent. They're both bonded to the same carbon. And because they're equivalent, the only difference being where the double bond is located, removing that hydrogen causes the remaining molecule, the conjugate base, to take on a resonance stabilized structure. That double bond immediately shifts into delocalized pi bonding, and consequently that delocalized pi bonding causes resonance stabilization, which makes the conjugate base more stable, further strengthening the acid. Interesting, right? Can I just tell you right now, I'm going to put that on your test and most of you are going to miss it. Like this. No, you're still going to miss it. So guys, what we're saying is this. We originally had this. We had this carbonyl group, this carboxylic acid group. Let's just make it vinegar. So this is now acetate. And when we pull the hydrogen off of acetate, functioning as an acid, oh gosh, when we pull the hydrogen off of acetate, the thing that's left over, the acetate ion, is actually resonance stabilized. That double bond does no longer exist there. It exists as a delocalized pi bond that exists between the carbon and both oxygens. That's called resonance stabilization, and that stabilizes the conjugate base, making the acid stronger. You good? You're still going to miss it, but are you good? All right, go ahead. It makes it harder for the hydrogen to go back. So when the hydrogen goes away, when that acetate becomes stabilized, that acetate is now going, I don't need you anymore. I'm better by myself than I was because I can sort out my bonding issues by creating delocalized pi bonding rather than wanting that hydrogen to come back. Yeah.
So electronegativity influences the polarity, right? The electronegativity of like oxygen to pull the electrons toward itself.
Okay. I would agree.
Yeah, okay, so then I'm just confused about the influence of the strength.
This has nothing to do with strength. This entire conversation that we had about oxyacids has nothing to do with strength. As if it was strength, they'd all have the same strength because it's always a hydrogen bonded to an oxygen. So when you're thinking oxyacids, and I know I'm steamrolling you right now, but let me just go for a second. When you think about oxyacids, it has nothing to do with strength. It's only about polarity.
I was just going back to, I thought electronegativity had to do with strength too, but
No, strength is a function of size. Polarity is a function of electronegativity.
so polarity doesn't affect strength at all.
Correct.
Okay.
Right. We think of them as being separate. You can, and it was your classic example of HF. HF has got a bond that's really stinking strong and really stinking polar. And so they function independently of each other. Yeah.
So we're kind of talking about two different types of strength.
Right, so we think of strength, but then we're also talking breakability. So strong bonds have low breakability, and polar bonds have high breakability.
So just like one type of the strength that you're referring to is the size, and then the other one is how much it is.
How easily it breaks, right? Yes, right. I know it's sort of a word game, right? Go ahead.
Will we ever be asked like which one has like stronger?
I don't know what you mean.
Oh, sorry, like the one you asked.
Which one from?
They won't ever like give us like a look and say like, is this pattern strong? Like or like expect us to be strong.
They could ask you stronger,
Yeah.
right? So let's do this.
Because it has to be something comparative, right?
So guys, let's do this now. Let's come back to where we started. So why is HCl a strong acid? So we go, well, yes, but why? So hold on, the first thing we got to do is go binary or oxy? Binary. So now what do we think about? The strength of the bond, which is a function of what? The size of the chlorine.
Chlorine's big, so it's
So chlorine is big, the bond is weak, the acid is strong. Now, HF, binary or oxy? Binary. So fluorine is small, the bond is strong, the acid is weak. Good. Now, NaOH, binary or oxy? Oxy. Sodium is a metal, the bond is ionic. Right? So guys, it goes like this. Sodium is a metal, the bond is ionic. But it's not the OH bond, it's the NaO bond. So the bond between the Na and O is ionic, therefore this is a base. Okay? Now we look at this. Here's our acidic hydrogen. This is an oxyacid. Why is this a weak acid and not an alcohol? Because of drift. It actually looks like this. And so this oxygen causes drift. What does that do to the OH bond? Makes it polar, thereby more easily broken. It is a weak acid. Now guys, what about this? CH3OH. That is an alcohol. Which bond breaks? None of them. None of them. Water does not, it does dissolve, but these bonds don't break. So guys, why is this bond not susceptible to breaking? There's no drift. Carbon is not electronegative enough to create drift. Consequently, the polarity of that bond is relatively low. Therefore, it doesn't break very readily, and this is an alcohol. Yeah, because this is a metal. And remember, it's like a chain. Chains always break at their weakest link. Here the weakest link is this bond because it's ionic. Here the weakest link is here because of drift. Here there isn't a weak link because there's no drift. Here you mean? It is shifted slightly towards the oxygen because oxygen is slightly more electronegative, but not enough to appreciably weaken the bond. Okay, now guys, go ahead.
Why does stronger, like higher polarity, equate to more breakability? Like with the OH, it's polar than H would like fall off.
Yeah, so the question, did you hear Matt's question? Why does greater polarity lead to greater acid strength? Guys, the answer to the question is this. What do acids do? Well, they give away hydrogens. Where do those hydrogens go? To water, right? And so think about it this way. If this It's sort of a mess, but you'll get the idea. If this region of electron density is shifted in this direction, it makes that proton even more naked. And as the shielding of that proton decreases, it's all the more attracted to the unbonded electrons on a water, and eventually this thing becomes so unshielded that it just lobs onto those electrons and it forms a bond in the other direction. And that's why, because as that polarity increases, those electrons move so far away that it just becomes easy pickings for water.
So it's like actual nitrogen bond.
Right, yes, that's right.
It's really attracted to the electrons on the water.
Correct, yeah. So guys, here's the trick. I wrestle every year with whether we should even talk about Lewis acids and bases. We don't have time to do that right now. Frankly, it doesn't buy us much anyway. So what I want to do is I want to just give you your homework. And then what we'll do is we will come back Thursday and we may or may not talk about Lewis acids and bases. With that said, and it's not a big assignment, right? If you have not done your chapter 17 outlines yet, we need to. We are really close to chapter 17. Let me look. Based upon your grunting and groaning, I'm guessing this is a busy time. So let me look. So guys, we are starting chapter 17 on Thursday. And as I'm thinking about this, I'm having a hard time imagining you coming in here Thursday without at least having looked at chapter 17. So guys, if you need a little wiggle in terms of the thoroughness of your chapter 17, let's do this. Please look at 17.1 and 17.2 and do what you would do with that relative to a summary. And then if you need the long weekend to complete it, let's do this. Guys, your chapter 17 summaries are due on Tuesday. With the commitment that you look at 17.1 and 17.2. Fair? Okay.